Indoor environmental quality is the fifth category of the LEED version 3 2009 Building Design and Construction Manual. It's the last section before innovation and design. It has 3 prerequisites that are mandatory for every project, starting with minimum indoor air quality performance, environmental tobacco smoke, then minimum acoustical performance. Now that third prerequisite is only required for schools. Schools is the most heavily weighted in this category. And once again, that's for the health of children. It's important for all of us, but kids are most susceptible to the chemicals that are being banned and not permitted in these credits. Here the credits are continued. We'll go through each one of these. You could see starting on IEQ credit 3.1, we're even talking about construction air quality management. So this is not only for building occupants, but also people constructing our buildings, which is very important. This section of the environmental quality credits 4.1 through 4.6 all have to do with low emitting materials. So that's setting limits to the VOCs being emitted, or in some cases, formaldehyde in the products. The last two, 4.5 and 4.6 for furniture and furnishings, and ceiling and wall systems have to do with schools only. But it's important to take into consideration for all building types. You can see towards the end of this section, we're going to talk about controllability of systems. So not only health, but also comfort comes into play and tenant interaction with the buildings. This section ends with daylighting, acoustics, and mold prevention. IEQ credit 9 and credit 10 have to do with schools only. Notice that daylight and views having to do with daylighting, and there's daylight and views that have to do with actually line of sight and views, and these are both more heavily weighted for schools as well. They've actually proven that kids perform better in buildings that have good daylighting and good indoor air quality. And it's true for adults as well. Indoor environmental quality is a very important component of green building design and construction. We've seen bad examples of what not to do and why we need to be really aware of what we're putting in our buildings. This happened with the drywall that was imported with China that we found was very unhealthy for our buildings and cost millions of dollars to rip out of buildings and reconstruct after we saw that the drywall was causing corrosion of our mechanical electrical system wiring. As you see that copper penny compared to that black wire, that wire used to be copper like that penny. So imagine what that was doing to our lungs. It's very important that we don't just purchase our materials based on costs, but actually know what's going into these building components, because the long-term costs on our health could be way more consequential. ASHRAE 62.1 2007 is a really important standard to know for the environmental quality section of LEED. The standard specifies the minimum ventilation rates and contaminants that can affect air quality, including chemical, physical, and biological factors. What's not included is thermal comfort. That's ASHRAE 55, which is addressed later in this section. So the standard takes into account the density of people within an area, the type of activity that is expected to occur in the space, and the nature of the ventilation air delivery system. So how a building is being used is really important in how you size and pick this equipment and how you're going to ventilate your buildings and keep a healthy indoor environmental quality. The first prerequisite is minimum indoor air quality performance. So this is required for all LEED buildings since it is a prerequisite. It references that standard, ASHRAE 62.1 2007, and at minimum has to meet the requirements of section 4 through 7 of that standard that sets ventilation for acceptable indoor air quality. This is without addenda, but with errata. Core and shell projects need to be able to meet the projected ventilation levels based on anticipated tenant requirements. There are defaults you can reference in the LEED reference manual to help you calculate this on an actual project. And to implement this, you want to use the ventilation rate procedure shown on the next slide. Minimum ventilation rates in your breathing zone provides information by occupancy category to determine both the amount of outdoor air needed to ventilate. So this has to do with people-related source contaminants, which is your occupancy density and activities, and also area-related source contaminants. And this includes off-gassing of building materials and furniture. So this has synergy with the low-emitting material credits later in this section. Zone air distribution effectiveness has adjustment factors for the breathing zone, outdoor airflow. These are all tables in the LEED reference manual. And then table 6.3, system ventilation efficiency, shows multi-zone systems and adjustment factors for outdoor air intake flow. This is a very technical section of LEED, so it's important to review these. Requirements for Case 2 naturally ventilated spaces must comply with ASHRAE Standard 62.1, paragraph 5.1. Once again, memorize these standards for the test. Anything in orange is something I'm emphasizing as more important and should be reviewed. Based on the location size of ventilation openings, spaces shall be permanently open to and within 25 feet of operable wall or roof openings. So making sure that if you're naturally ventilated space, that people have access to the openings where that natural ventilation and fresh air intake is happening. And the operable area must be at least 4% of the net occupiable floor area. Opening between rooms applies if 8% or 25 square feet is free. For mixed mode ventilation, that includes mechanical systems and natural ventilation techniques, the requirement comes from ASHRAE 62.1, Chapter 6. And in this case, any acceptable calculation can be used that meets that standard. Remember to actually memorize which chapter of ASHRAE correlates to each option. Next slide. Calculations. Page 411 in the reference manual has examples of this. If you're working on a real project, I definitely encourage having the reference manual and being able to check these reference manual pages, although it's not required for the exam. Breathing zone outdoor airflow is the amount of airflow required in the occupied spaces. The calculation for breathing zones serviced by mechanical ventilation systems is the breathing zone outdoor airflow equals the sum of the required per person outdoor airflow rate times the zone population plus the per unit required outdoor airflow rate times the zone floor area. Now, if you're a mechanical engineer, this probably makes a lot of sense to you, but if not, you really are going to have to review this section carefully. And we'll look at some case studies as well. Zone outdoor airflow equals the breathing zone outdoor airflow calculated above divided by the zone air distribution effectiveness. Once again, if you're not a mechanical engineer, just try to memorize these relationships. You don't have to do a lot of calculations on the exam, but you have to understand the concepts of the calculations. Benefits include improvement in occupant comfort, well-being, and productivity. As I mentioned, there are studies that show that people work better, students learn better in buildings with good daylighting, good ventilation, equaling healthy indoor environmental quality buildings. Also reduces potential liability regarding indoor air quality issues for architects, builders, owners, building operators, and occupants. So once again, LEED is about really being future ready. It is optional to get the certification, but codes, mandatory provisions are actually moving this direction to meet some of this LEED criteria. You see this in California in the Cal Green Code, and even in Oregon you could see our REACH code is starting to incorporate some of these LEED requirements. And so it really is about healthy indoor environments and avoiding liability issues in the future from tenants actually saying their building is making them sick. This is the last thing you want to happen as a designer or building owner or even contractor. Related credits, there's many synergies among these credits to be aware of as we go through this section. The second prerequisite for the indoor environmental quality section is environmental tobacco smoke, also known as ETS control. This is required for new construction, schools, and core and shell. Case 1, option 1, is for new construction core and shell, and it requires that you prohibit smoking in the building and locate any exterior designated smoking areas at least 25 feet away from entries, outdoor air intakes, and operable windows, and provide signage. So remember that 25 feet applies in two ways. For natural ventilation, occupants have to be within 25 feet of operable windows. And similarly, you have to locate smoking areas 25 feet away on the exterior of these operable windows. So notice that connection. Next slide. Option 2, new construction core and shell. Want to prohibit smoking in the building except in designated smoking areas. Exterior designated areas must be at least 25 feet away from entries, outdoor air intakes, and operable windows, and provide signage. Interior designated smoking rooms must contain, capture, and remove environmental tobacco smoke from the building. So in this option, you can have smoking indoors, but the criteria for these designated areas is very important to understand and actually memorize for the exam. And here's the criteria. These rooms must directly exhaust outdoors with no recirculation, so make sure that engineers on a project understand this criteria. Contractors need to understand that it must be enclosed with deck-to-deck partitions and must be able to create a negative pressure of an average 5 Pascal with a minimum of 1. And also you must verify by conducting 15 minutes of measurement with a minimum of 1 measurement every 10 seconds. This also correlates to the commissioning of these systems. The verification process is critical for these LEED prerequisites and credits. That's really what LEED's about, is verifying best practices in building design and construction of green buildings. Next slide. Case 2 is for residential and hospitality projects. Requirement is to prohibit smoking in all common areas of the building, prohibit on-property smoking with same parameters as case 1, locate exterior designated smoking areas, including balconies, to meet the same requirement as case 1, weather strip all exterior doors and operable windows and units, minimize uncontrolled pathways for environmental tobacco smoke to transfer between units. If you have a smoker in an apartment or condo or hotel room next to a non-smoker, you want to make sure that the person next door is not getting secondhand smoke. So you need to seal penetrations in walls, ceilings, and floors in the residential units, and by vertical chases. And doors need to be weather stripped to minimize air leakage. So infiltration is what we're trying to avoid. And a blower door test is a good way to demonstrate acceptable sealing. In Oregon, the Energy Trust of Oregon actually helps perform these type of audits and testing. So check with your local jurisdiction to see if there's any resources or funding for these type of practices for green building. For schools, indoor smoking areas are prohibited. You also need to prohibit on-property smoking within 25 feet from entries, outdoor air intakes, and operable windows. And you also need to provide signage to indicate designated and prohibited areas. The standard for the blower door test criteria is ANSI ASTM, standard test method for determining air leakage rate by fan pressurization. For residential, there's a manual for compliance with California's 2001 energy efficiency standards. California Code has really upped the ante in their building requirements. You want to look at Progressive Sampling Methodology, Chapter 4. Resources can be found on the following link. The image shows a blower door test going on and the equipment required. Check with your local contractors to see who will perform these type of procedures before you hire them. The third prerequisite for indoor environmental quality is for minimum acoustical performance. It only refers to schools. And the requirement is to include sound absorbing finishes that comply with ANSI standard S12.6 acoustical performance criteria, design requirements, and guidelines for schools. This indicates that the maximum background noise level from HVAC systems is 45 decibels in classrooms and other core learning spaces. For case 1, which are classrooms and core learning spaces less than 20,000 cubic feet, option 1 is to confirm that 100% of ceiling areas except lights, diffusers, and grills have a noise reduction coefficient of 0.7 or higher. Having a good acoustical performing ceiling finish will really help diffuse background noise. Option 2 is to confirm the total wall panels, ceiling finishes, and other sound absorbing materials equal to or greater than total ceiling have a noise reduction coefficient of 0.7 or higher. So if you can't meet the 100% criteria in just your ceiling finish, you can add wall boards and panels as well to help with this acoustical performance, as long as the aggregate total equals 100% of the ceiling square footage. Case 2 is for classrooms and core learning spaces greater than 20,000 cubic feet. You need to verify through ANSI standard S12.6 calculations that classrooms have reverberation times of 1.5 seconds or less. Too much reverberation time in a room causes echo. Here's an example chart of various materials and their acoustical coefficient. You don't have to memorize this chart, but it's good to compare materials to start to see which ones perform better. Something like concrete that's really hard, solid, has a very low coefficient, whereas something like down below that, under floor, you could see carpets have a much higher coefficient, so they're going to absorb the echo and sound reverberations better. Strategies include using high NRC ceiling tiles, add sound absorbing panels on the side and rear walls, have sound absorbing panels on the side, rear walls, and ceilings in rooms taller than 11 feet, and use carpeting to reduce noise from chairs and people walking. On the right, you see examples of sound absorbing panels that also look like art, so it can help with their aesthetic. So performance and form can go hand in hand. And another synergy can be cork panels that are actually rapidly renewable as well, that have synergy with material and resource credit. More strategies for reducing background noise include adding storm windows that are better insulated, use thermally insulated windows, which helps with energy performance, so synergy with optimizing energy performance, energy and atmosphere credit as well. Check doors for gaps larger than 1/16 inch. Use drop seals and gaskets. And use sound control doors for rooms near noisy areas. So once again, isolating those areas so the noise doesn't penetrate. This is really important for classrooms, which is why it's required for schools. Strategies for reducing HVAC noise include not installing fans, compressors, and other HVAC machinery near classrooms. So location pre-design is key. So coordinating with architectural designs and engineering requirements for HVAC is very important. Service and balance HVAC systems. Commissioning can help with this process. Build custom sound enclosures around each unit. Use sound line ductwork. Insulating ductwork can also help with energy performance, depending on what is actually insulating the ductwork. The example shown is more for acoustics. Replace older units with quieter systems. Boost the open area at grills and diffusers. Lengthen ducts to reduce noise. So less pressure usually has less noise. Use separate HVAC ducts for classrooms. It's important to approach these strategies in a comprehensive way. For documentation, you need to include installed surface areas of sound-absorbing materials, reverberation times, and document methods used to keep background noise levels below 45 decibels. Also keep manufacturer's data sheets on the noise reduction coefficient for each acoustical finished material. You don't want to look like this guy with a headache.